Thank you.
Yes, sir, you can start.
Okay, thank you. Now we are going to discuss about fluid mechanics and hydraulic machinery. So first of all, I'm going to explain about the fluid mechanics. After that, I'm going to give the explanation about the hydraulic machinery. So first of all, basically, what is FM and HM? So what is the meaning of fluid mechanics and what is the meaning of hydraulic machinery? So here I am saying clearly, so fluid mechanics always deals with fluids which are under rest or which are under motion. That is named as fluid mechanics. So before going to analyze fluids which are in rest condition, which are in motion, first of all we are going to know what is the fluid, how many types of fluids we are having. So how to know the properties of the fluid and how we can apply these properties of fluids. So where we use these properties, with application one by one. So please listen carefully. What is the difference between FM and HM? So here, in case of fluid mechanics, we are going to calculate three variables. That is, first one is nothing but pressure, and the second one is nothing but, please, second please. Right. So here we are going to discuss about 3 points in fluid mechanics. So please take care about. First one, we are going to learn how to calculate pressure and how we can measure the pressure. That is the first variable we are going to calculate in our FM, fluid mechanics. When the fluid is said to be under rest condition or the fluid is said to be under motion, whatever the condition we are having, we are going to calculate what is its pressure. What is its pressure? And the second one, we are going to calculate. So please take care about that one. So I will write on this board. Right. So first one is nothing but pressure, and the second one is nothing but velocity of the fluid. Velocity of fluid. After calculation of pressure, now I am going to calculate what is the velocity of the fluid. After knowing the velocity of the fluid, I'm going to find what is the force exerted on the fluid. So I'm going to find what is the force on fluid. That is how much force is exerted on a fluid. By the application of this force, the fluid is said to be under motion. So here in our fluid mechanics, we have to calculate first one pressure, second one velocity, and the third one is nothing but force. Now, if you know the value of force, automatically we can calculate work energy. That is next one. I'm going to give it to you. So next one, I'm going to give it to you. Fourth one is nothing but work, and fifth one is nothing but power, and sixth one is nothing but efficiency. Now, if you know how to calculate, if you know how to calculate pressure, velocity, and force on a fluid, so then I'm going to write the relation between these three variables. Then we are getting the work and the power and efficiency. What is the work here? Work is nothing but force into displacement. And what is the power here? Power is equal to work by time. If you know how to calculate force and is multiplied by displacement, then we can get the work energy. If you know the work energy, I can calculate what is the value of power. If you know the power here, I can find the efficiency. Efficiency is nothing but so power output divided by power input. Now, in fluid mechanics in FM, we are going to calculate so what is the value of pressure, velocity, and force exerted on the fluid when the fluid is said to be under motion or when the fluid is said to be under rest condition. That analysis is named as fluid mechanics. So, what is the meaning of fluid mechanics? It is the study of fluids which are under static condition or motion is named as fluid mechanics. Now, what is hydraulic machinery? Now, if you know calculation of pressure, velocity, and force, then I'm going to write the relation between these variables. I'm getting these some equations. What are the equations here? I'm writing here. What are the equations we are having? All of you know very clearly. So first one is nothing but continuity equation. First one is continuity equation, and the second one is nothing but Bernoulli's equation, and third one is nothing but impulse momentum equation, and the fourth one is nothing but moment of momentum equation. Moment of momentum equation. So these are the different types of equations we can use. So in our fluid mechanics, but I'm going to apply these equations on different types of devices. What are the devices we are using here? Turbines, pumps, nozzles. So this type of devices we are using in our fluid mechanics. I'm going to apply these equations on those devices. I can calculate what is the work done by the system and what is the power developed by the system and what is the efficiency of the system. Now, these are nothing but application of these equations on different types of devices. So, application is nothing but HM, that is nothing but hydraulic machinery, and basics is nothing but fluid mechanics. What is the basics here now? In basics, we are going to learn how to calculate pressure, velocity, and force. So that is nothing but fluid mechanics. Now I want to give it to you what is the basic difference between fluid mechanics and strength of material. I want to give what is the difference between fluid mechanics and strength of material. So first of all, what is matter here? So in our nature, matter can exist in two forms. In our nature, matter can exist in two forms. One is named in the form of solid and one is in the form of fluid. One is in the form of solid and another one is in the form of fluid. Now, in case of solids, we are having different types of materials. That is elastic material, plastic material, and a rigid material. There are different types of materials. So, but we are most of the cases we are using elastic material. Why? Because it follows Hooke's law. Because it follows Hooke's law. So, in case of solids, we are going to apply different types of forces, that is tensile force, compressive force, bending force, and shear force, and twisting force. So these are the different types of forces I can apply on a solid material. The material may be elastic material or plastic material or rigid material. So we can apply tension, compression, bending, shear, twisting. So by the application of these forces, I want to calculate what is the stress in the material and what is the strain in the material and what is the relation between the stress and strain in one dimensional, in two dimensional, and in three dimensional. Then this analysis is named as solid mechanics. This analysis is named as solid mechanics. I'm giving very clearly what is the difference between solid mechanics and fluid mechanics. In solid mechanics, we are going to analyze the what is the effect of tension, compression, bending, shear, twisting. By the effect of these forces, what are the values we have to calculate in that material? What are the values we are going to calculate in that material? One is stress, next one is strain. If you know what is the value of stress and strain in a material by the application of different types of forces, then I'm going to write the relation between the stress and strain in one dimensional, two dimensional, three dimensional. Then this chapter is closed. That is named as solid mechanics. This is named as SOM also or solid mechanics. Now, what is fluid mechanics here? So here, different types of solids, elastic, plastic, rigid. So those are different types of solid materials. But in case of fluid, we are having different types of fluids. The fluids are in two form. One is in the form of liquid and one is in the form of gas. One is in the form of gas. So if we take a liquid, if we take a gas, on the liquid, on the gas also, we are having some forces. First one, gravity force. Second one, pressure force. Third one, viscous force. Fourth one, compressibility force. And the fifth one, turbulence force. And next one is surface tensional force. And next one is elastic force also there. So these are the different types of forces which are related to fluids. But in our nature, fluids are exists in two forms. One is in the form of liquid, one is in the form of gas. So I want to find the what is the gravity force on this liquid or gas, what is the pressure force on the liquid or gas, what is the viscous force on liquid and gas. So I want to calculate these forces. So if you know these forces, I can calculate what is the work energy, power and efficiency of any system or any type of fluid which is flowing through any system. Now here, by the application of these forces, I want to find what is the pressure and what is the velocity and what is the force exerted on the fluid. These are the variables we are going to find in fluid mechanics. These are the variables we have to find in our strength of material. That is the difference between the solid mechanics and fluid mechanics. Now, the study of pressure is nothing but statics. So, in this chapter of statics, we are going to learn what is the definition of pressure, what is the units of pressure, and what is the measurement of pressure. We are going to study in statics. So, I will give the later what are the classification of fluid mechanics. I will give later also. So, but we have to learn what is the difference between these two. So, in case of solids, there are different types of force are acting. In case of fluids, there are different types of force are acting. We know that we can calculate gravity force, pressure force, viscous force, compressibility force, turbulence force, surface tensional force. I can give very, very clearly how to calculate these forces during our analysis of fluid mechanics. After calculation of pressure, velocity, force on a fluid, I want to apply those formulae or equations. What are the equations we are having? Continuity equation, impulse momentum equation, Bernoulli's equation, moment of momentum equation. I can apply these equations on different types of devices. I can find what is the work done by the system and what is the power developed by the system and what is the efficiency developed by the system. I can find very easily. So this is the basic difference between solid mechanics and fluid mechanics. So we are going in fluid mechanics, we are going to deal with the two types of fluids. One is liquid and one is gas. I will give it to you very clearly. This liquid is also named as incompressible fluid and gas is also named as compressible fluid. A liquid is named as incompressible fluid. Gas is also named as compressible fluid. I will give it to you. Why we are going to name it as incompressible? Why we are going to name it as compressible fluid? What is the difference between these two, compressible and incompressible fluids? So all liquids are belongs to incompress. All gas are belongs to compressible fluids. But what is the uh, meaning of incompressible and compressible fluids? So I'll give it to you. So please take care about that one. So if you take a fluid in a small vessel, maybe liquid or gas. For example, I am taking a small vessel which is fitted with a piston, which is fitted with a piston. I am taking some quantity of liquid here, first of all. Now it is having some volume, it is having some properties also. Pressure, volume, temperature. There are different types of properties contained by the fluid. Initially, it is having volume of V1. If you apply the force in this direction, then what happen? Automatically, volume will reduce. So, what is the final volume here? The final volume is nothing but V2. What is change in volume? If you observe this diagram, then if you apply the compressive force in vertically downward direction, its volume will reduce. So change in volume, I'm writing change in volume of liquid, we are getting negative. Why? Because we are always writing V2 minus V1. We are always writing V2 minus V1. V2 minus V1 is we are getting negative value. So check this value, how much we get it. Okay, right. Now I'm going to replace this liquid by gas. Liquid by gas. Apply same amount of force as same as applied on the liquid. That means I'm applying the same force on liquid on gas. I'm going to check its change in volume. Now, if you apply the same amount of force on the gas, then the volume of the gas will also changes from V1 to V2. Now I'm writing here the change in volume of the gas is also is equal to negative. That is also V2 minus how much? V1. Have you got it? Now, after getting the change in volume of liquid and change in volume of gas, compare these two values. Which value is very, very less? So if you compare these two values, the change in volume of the liquid is very, very, very less when compared to gases. So I'm writing here, the change in volume of liquid is very, 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 very less than the change in volume of the gases. So that the change in volume of liquids is negligible. So that what I am saying, we are going to consider the change in volume of liquids is negligible when compared to gases. That's why the liquids are named as incompressible fluid. The liquids are named as incompressible fluid. But practically in our nature, liquids and gases both are compressed. Liquid and gases both are compressed, but we are going to take it as in case of liquid that compression of the liquid is very very less when compared to gases, so we are going to neglect that one. So that's why the liquids are named as incompressed, gas are named as compressible fluid. So that is the meaning of incompressible fluids and compressible fluids. And I hope you understood this one. What is the difference between liquids and gases? So at the same time also, when density changes is very, very less, and density changes in gas are also more when compared to liquids. So I can compare these two fluids in two terms. One is said to be in the form of volume, and one is said to be in the form of density. So when the density of the with change in density of the liquid is very very less when compared to gases, the change in volume of liquid is very very less when compared to gases. That's why the change in density, change in volume is very very negligible value in case of liquids. That's why these liquids are named as incompressible fluid and the gas are named as compressible fluid. But practically both are compressed. That means liquid also having compressibility and gas is also having compressibility. We can find what is the compressibility of liquids. We can find what is the compressibility of gases. So in case of fluid mechanics, we are going to deal with what is the analysis of incompressible fluid, what is the analysis of compressible fluid. That is, we are going to analyze what is the pressure, velocity, force, work, power, efficiency of liquids as well as gases. We are going to discuss now. So first of all, I'm going to explain what is the analysis of incompressible fluid. Before going to analyze the liquids and gases, I'm going to give it to you. What is the definition of fluid mechanics and what is the classification of fluid mechanics and what is the definition of fluid? What is the difference between the solid and fluid? In case of solid, I'll give it to you one by one. So please listen carefully. So I hope you understood what is the difference between solid mechanics and fluid mechanics. And at the same time, I hope you know what is the difference between the FM and HM also. In this case of FM, we are going to learn how to calculate power, efficiency, and work and pressure, velocity, and force. So we are going to learn those values, how to calculate. And after that, I'm going to combine those values to convert into equations. That equations are continuity equation, Bernoulli's equation, impulse momentum equation, momentum equation. I want to apply those equations on devices. That application is nothing but hydraulic machinery. So I can apply any equation, Bernoulli's equation, impulse momentum equation, continuity equation. So I can find what is the work done by the system and what is the power developed by the system, and what is the efficiency developed by the system. I can calculate it very easily. Okay, right. So this is the basic difference between fluid mechanics and solid mechanics. So now I'm going to explain what is fluid mechanics. All of you know very well what is fluid mechanics. So fluid mechanics is a branch of science. So listen carefully. It is very, very simple subject. So if you follow me, so I will give you an easy way to understand the fluid mechanics. So fluid mechanics is a study of fluids. So fluid mechanics, FM. What I am saying here, study of fluid properties or fluid behavior, study of fluid behavior, which are in rest or motion. So this is the definition of fluid mechanics. Now, the fluid mechanics is classified into three parts. I have already told you. In fluid mechanics, we are going to calculate three variables. So that I'm going to divide this fluid mechanics into three parts. That is nothing but a classification of fluid mechanics. Classification of fluid mechanics. First one is nothing but statics, and the second one is nothing but kinematics, and third one is nothing but dynamics. Now listen carefully what I am saying here. So we are going to deal with statics, we are going to deal with kinematics, we are going to deal with dynamics. In case of liquids, in case of gas also. So in statics, we are going to deal with pressure. We are going to deal with pressure. When the fluid is said to be under rest, when the fluid is said to be under motion, what is the pressure contained by the fluid? Or what is the pressure at any point in a fluid when the fluid is said to be under rest, when the fluid is said to be under motion? That is nothing but static condition. That means actually when the fluid is said to be under motion, so that is not belongs to statics. Why I'm telling you that thing now? That means if you take a small pipe, when the fluid is passing through the pipe in this direction, between the point one input and output. So between the input and output, the mass is remains constant, and the flow is also constant. The flow is steady flow. That means how much mass is entered here, same mass will leave here. That means between section 1 and 2, I'm going to consider the fluid is said to be under static, but it is under motion. Between 1 and 2, I'm going to consider as a static fluid. But I can find what is the pressure of the fluid at input, what is the pressure of the fluid at output. I can find it. But this fluid is said to be under motion, but between 1 and 2, I'm going to assume it as a static condition. That's why I'm saying here. So in statics, we are going to calculate what is the pressure of the fluid. What is the definition of pressure and what is the units of pressure and what are the devices we are going to use to calculate the or to measure the pressure. That is nothing but statics. I'm going to give it to you very clearly how to calculate the pressure of the fluid. So in the in the later discussion. Now what is the kinematics here? Kinematics is nothing but study of fluids which are under motion. So in this case, the fluid is at rest condition. But in kinematics, we are going to take the fluid which is under motion, which is under motion. When the fluid is said to be under motion, when the fluid is said to be under motion, automatically it is having some velocity. It is having some velocity. Are you got my point? So when the fluid is under motion, it is having velocity. If you know how to calculate velocity, immediately I can calculate what is its acceleration. What is its acceleration? What is acceleration here? That is change in velocity with respect to time. That is dv by dt. So that is nothing but acceleration. So in case of kinematics, we are going to deal with fluids which are under motion without consideration of forces which is applied on the fluid, which is applied on the fluid. When the fluid is said to be motion, by the application of some external force only, the fluid is under motion. If there is no external force, the fluid is said to be under static condition. The fluid is said to be under static condition. When the fluid is under motion, there are 2 points are there. One is due to gravity force, the fluid automatically flows from high pressure to low pressure. And again, another one is if you maintain the pressure, for example, if this is input and output, this pressure is P1 and this pressure is P2, and P1 is greater than P2, automatically the fluid flows from high pressure to low pressure. That is the property of the fluid, right? So if the P2 is more than P1, then the flow takes place from 2 to 1. If the P1 is more than P2, the flow takes place from 1 to 2. So what is the property of fluid? It flows from high pressure to low pressure. If you want to maintain the flow, if you want to maintain the flow, we have to maintain the pressure at one point is more than the other point. Automatically the flow takes place. Automatically the flow takes place. When the flow takes place, then it is having velocity, it is having acceleration. I want to find its velocity, I want to find its acceleration. When the fluid is said to be under motion, there are different types of motion of the fluid or different types of flows of the fluid. When the fluid is under flow, when the fluid is under flow, that flows are different types. All of you know steady flow, uniform flow, laminar flow, rotational flow, and compressible flow. Compressible, incompressible, rotational, irrotational. Next one is laminar turbulent flow, steady flow, unsteady flow, uniform flow, non-uniform flow. These are the types of flows contained by the fluid by the application of the external force only. Right? Now we are going to discuss about dynamics. What is dynamics? In dynamics also, we are going to consider what is the motion of the fluid. When the fluid is said to be under motion, we are going to calculate how much force is exerted on the fluid. We are going to calculate, but here we are not consider how much force is acting on the fluid. That means study of fluids which are under motion without consideration of forces which are acting on the fluid. That is nothing but kinematics. But in case of dynamics, we are going to analyze the fluids which are under motion with the consideration of external force. If we consider the external force, I want to find that force. I want to find that force. What is that force now? Force is equal to how much? M into A according to your Newton's second law. According to your Newton's second law, F is equal to how much? M into A. So I can find the acceleration according to your kinematics. I can find the mass of the fluid. The mass of the fluid is multiplied by acceleration. Then I can find how much force is acting on the fluid. If you know the force, I can find the work, I can find the power, I can find the efficiency. So in case of dynamics, I can find how much force is exerted on the fluid and how much work done by the fluid, how much is powdered by the fluid, or what is the efficiency of the system. We can find anything in fluid dynamics. So this is the classification of fluid mechanics. So basically, fluid mechanics is divided into three groups: statics, kinematics, and dynamics. Now we are going to discuss about what is statics, kinematics, and dynamics of fluids. Right. So before going to discuss about these three statics and kinematics and dynamics, I want to give first of all what is the definition of a fluid. What is the definition of fluid? How many types of fluids we are having? How many types of fluids we are having? So I'll give it. Listen carefully here. Now I'm going to give what is the difference between solid and fluid. For example, I want to define what is the definition of fluid. What is the definition of fluid? So, fluid is a substance. Fluid is a substance which is in the form of liquid or gas, which is in the form of a liquid or gas, which deforms continuously in the direction of flow under shear. Listen carefully, very clear. I'm saying very clear. So, fluid is a substance which deforms liquid or gas, which deforms continuously, continuously by shear stresses. Fluid is a substance which deforms continuously by shear stresses which are present in the fluid. Which are present in the fluid. I will give the explanation what are the shear stresses in fluid. I will give it to you explanation. Listen carefully. What is the fluid? If you apply the force on a fluid or if you maintain a pressure difference between one point to another point, automatically the flow takes place from high pressure to low pressure. Then what I am saying here, then when the fluid is said to be under motion, it deforms continuously. It deforms continuously by the shear stresses or shear forces. That is the definition of fluid. Now, I'll give a simple difference between solid and fluid. If you take a solid, if you take a solid, I can apply different types of forces on the solid: tensile, compressive, bending, shear, twisting. There are different types of force I can apply. If you apply any type of force on this one, the material will deform or material will extend. Suppose, for example, when the material is deformed, if you remove the external force, if you remove the external force, when the material is deformed by the application of external force like this, when the material is deformed by the application of external force like this is the deformation of the material after application of the force. This is the deformation condition. If you remove the external force, this is the external force, not internal force. Internal force is nothing but resisting force. So every material having internal force, that internal force is always named as resisting force. Please take care about that point. So we are applying the external force. That external force is nothing but P. Internal force is nothing but R. R is nothing but internal resisting force. If you apply some external force on the material, material must be under deformation. If you remove the external force, the material regains or comes to original position. That is named as elastic material. But in case of fluid, if you apply the force on the fluid and it undergoes some deformation, but if you remove the external force, the fluid never comes to original position. That means it deforms continuously. That's why I'm saying it deforms continuously. It deforms continuously. So please take care about that point. What is a fluid? Fluid is a substance which deforms in the direction of flow by shear stresses or shear forces. Right? So that is the difference between solid and a fluid. So in case of solid, if you remove the force, if it is elastic material, the material can easily comes to original shape or original position. That is named as a solid. So in case of strength of material, we are always using which type of material? Elastic material. Why? Because it always follows Hooke's law. That's why we are going to use always elastic materials in our nature. There are different types of elastic materials are there. So mild steel. So there are different types of materials are there in strength of material. So this is the definition of fluid. Fluid is a substance which is in the form of liquid or gas which deforms continuously by the shear forces or shear stresses. That is the definition of fluid. Now here the fluids are how many types? So fluids are two types. Fluids are two types. Generally, I am saying One is ideal fluid, and the second one is nothing but a real fluid. But there is no ideal fluid in our nature. There is no ideal fluid in our nature. It does not have any viscosity. It does not have any surface tension. It does not have any capillarity properties. That means simply we can say it does not have any viscosity and surface tension. So that fluid does not exist in our nature. That means if you use this fluid does not have any losses. That means no losses. This fluid having no losses. No losses means what is the energy at input E1? What is the energy at output E2? If E1 is equal to E2, what is the if E1 is equal to E2, then what is the value of losses? There is no losses. That means energy input is equal to energy output means both energies are equal means there is no losses. But in our nature, if you take any fluid or any system, every system having some losses. That means if the fluid having losses, that fluid is named as a real fluid. That means it is having some viscosity, surface tension, and capillarity properties. So that is a real fluid. Real fluid means there must be losses. There must be losses. That losses belongs to frictional losses or any other losses. So all of you know those losses are named as major losses and minor losses. All of you know very well what is the major loss and minor losses in our fluid mechanics. So major loss are belongs to frictional losses. Minor loss are belongs to general in case of pipes, certain expansion, certain contraction, or pipe bends, pipe fitting. There are different types of reasons are there for minor losses. But if compared to major and minor losses, major loss are always more than the minor losses. But we have to calculate both. But in some cases, we are going to neglect the minor losses. We are going to consider the major losses. So, what is a real fluid? A real fluid of fluid which is having viscosity, surface tension, right? That means which is simply we can say which is having viscosity. If there is no viscosity of the fluid, that fluid is named as ideal. That fluid is ideal, but the ideal fluid does not exist in our nature. If there is an ideal fluid, what is the efficiency of the system? If the energy input is equal to energy output, then I'm writing here efficiency is equal to output by input. We are getting how much percentage of efficiency? 100% of efficiency. That means there is no any device in our nature which can produce 100% of efficiency, which can produce 100% of efficiency. That means there must be losses. That means in our nature, all fluids are belongs to real fluids. All fluids are belongs to real fluids. There is no any ideal fluid. So ideal fluid means it does not have any losses. A real fluid means it is having losses. And at the same time, it does not have any viscosity. It does not have any surface tension. In this case, it is having viscosity. It is having surface tension. Unlike some. Right. So that is the different types of fluids. But in case of real fluids, in case of real fluids, again we are having two classifications. In case of real fluids, we are having again two types of classifications. One is Newtonian fluid. One is Newtonian fluid. And second one is nothing but non-Newtonian fluid. In case of real fluids, we are having again two types of classifications. Newtonian fluid is also having viscosity. Non-Newtonian fluids also having viscosity. But what is the difference between these two, Newtonian and non-Newtonian? Newtonian and non-Newtonian. That means in our nature, we are having so many types of liquids in our nature. So many types of liquids in our nature. Some liquids follows Newton's law of viscosity. I'll give the explanation what is Newton's law of viscosity. Right? What are the fluids follows Newton's law of viscosity? Those are named as Newtonian fluid. What are the fluids does not follow the Newton's law of viscosity? Those fluids are named as non-Newtonian fluids. non-Newtonian fluids. So now here we are going to discuss what is the analysis of Newtonian, what is the analysis of non-Newtonian fluids. Those fluids are belongs to liquids or gases, whatever it is. I got my point or not? So what I am saying here, in our nature, we are having all fluids are real fluids. There is no any ideal fluid in our nature. That means there must be some losses. Real fluids are classified into two types. I'll give the explanation. So please take care about these 2 points. What is fluid and what is the types of fluids here. So if you see the types of fluids, what are the fluids exists in our nature? Real fluids. Real fluids means it is having viscosity. If the fluid is having viscosity, it is having losses. It is having losses. I will give the explanation clearly. Right. So FM definition is over. Classification of FM is over. What is statics? What is dynamics? What is kinematics is over. And what is the definition of fluid is over. And what are the types of fluids is also over. And what is the difference between the solid mechanics and fluid mechanics also over. Right. Now I'm going to start with analysis of incompressible fluid. So before going to calculate pressure, velocity, force of liquids and gases, I want to know what are the properties of the fluids. What are the properties of the fluids? Or we can say simply fluid properties. Before going to know the fluid properties, these fluid properties are belongs to standard fluids. So we are having liquids, we are having gases in case of fluids, but here in case of liquids, in case of gases, in case of liquid, in case of gases, we are taking one standard liquid, one standard gas. If you know the standard liquid, if you know the standard gas, I want to know the properties of these two standard fluids. That means fluid properties of water and gas. So these two are, that is fluid properties of water and air. Air is nothing but standard gas. So in case of liquids, what is the standard fluid? That standard fluid is nothing but water. Here I am taking standard fluid is water. Why I am taking standard fluid is water? Why I am taking standard fluid is water? Because this water having very low viscosity. That is the first reason. Low viscosity. That is the first reason. Here is also low viscosity. Same. And the second one, availability of water is more. Availability of water is more. Here is availability of air is more. So here is the standard gas is air. So these are the two reasons we are going to consider water and air are standard fluids. In case of liquids, water is a standard liquid. In case of gases, air is a standard gas. Now we are going to discuss about what are the properties of water and what are the properties of air. If you know the properties of standard fluids, water and air, I'm going to compare the properties of remaining fluids with respect to the standard fluids. I'm going to compare it very easily. Is it right or not? Right? So that if you want to know the properties of fluids, the properties of fluids always belongs to water and air. Water and air. So, what is the reason for we are going to consider water and air standard fluids? Two reasons simply. These two are having very low viscosity. I will give it to you. What is viscosity? What is viscosity? So, water having low viscosity and gas is also having low viscosity. And what is the availability of water in nature? What is the availability of water in nature? Availability of water in nature is very high, and at the same time air is availability in our nature is also high. So this availability of these two fluids are very very high, so that we are going to consider the water and air are named as standard fluids in case of liquids and gases. Now we are going to discuss about what are the properties of water and the properties of gas. Right? After knowing the properties of these two standard fluids, now we are going to enter into the subject, that is statics. What is statics? Study of fluids under rest. Next one, kinematics. Study of fluids under motion. And again, we are going to enter dynamics. Study of fluids under motion with the consideration of forces. One by one, I'm going to explain to you. Please take care about these points now. Right? Now here, I'm going to give the basics of fluid mechanics, that is also named as fluid properties. That is chapter number one. This is a very important. In this chapter, only three properties are very important in any competitive exam. Remaining all are very simple, very easily we can understand, and we can solve the problems very easily also. But three properties are very important in competitive exams. So please take care about. I will give the explanation about all properties. So, but I will give more explanation about the important properties in our competitive exam, whether it is GATE or ESC or any ISRO, whatever it is. So please take care about the analysis of these properties of fluid. So first of all, I'm going to write the chapter number one, that is fluid properties. Chapter number one, fluid properties. So in this case, we are going to know the properties of water and air. I'm writing here water, air, right? Now listen carefully here. What are the properties contained by the water and air? So first one, if you take water or air, both are contains a property that is named as density or mass density. Density of the fluid or mass density of the fluid. This is the first property. Density or mass density of the fluid. Right? What is the definition of density or mass density? So mass density or mass density both are same. It is indicated by the symbol rho. Rho is equal to ratio of mass of fluid, mass of fluid to unit volume, unit volume of the fluid. That is mass of the fluid per unit volume of the fluid. Mass of the fluid per unit volume of the fluid. What is the mass here? Mass is always expressed in terms of kg and unit volume always expressed in terms of meter cube. That is the definition of density. Density is equal to mass by volume. Mass by volume. And the second one, specific volume. Specific volume. So it is indicated symbol small v. This is the property number two. This is the property number one. What is the specific volume here? Specific volume is always defined as a ratio of volume of fluid per unit mass. Volume of fluid per unit mass. So what is the volume? Volume is always expressed in terms of meter cube and unit mass is expressed in terms of kg. So if you observe this one and this one, both are reciprocal to each other. So I am writing simply specific volume is equal to 1 by rho. This is the relation between the specific volume and density. Are you got it? So this is the second property, specific volume, and the first one is density or mass density. So these two properties are very simple for any type of fluid we can calculate. So anyone, if give any two variables, you are having three variables, one, two, three. If any two is given, then we can find other one. So these are the property number 2. And the third one is nothing but property number 3. That is nothing but specific weight. That is nothing but specific weight of the fluid. Specific weight of the fluid. Now, how to calculate specific weight of the fluid? So, weight is expressed in capital. Weight is always uh, indicated by the capital W, and the specific weight is indicated by the small w. Total weight is capital W, specific weight is small w. Right? So, specific weight is defined as specific weight is equal to it is the ratio of weight of the fluid. It is a ratio of weight of the fluid per unit volume of the fluid. Unit volume of fluid. This fluid, what is the weight of the fluid here? Weight is always measured like m into g. Weight is nothing but m into g. And volume is nothing but v. But what is m by v? M by is nothing but mass by volume. That is nothing but rho g. Then what is the formula for specific weight here? Specific weight is equal to rho into g. Specific weight is nothing but rho into g. This is specific weight. Then what are the units here? Density is expressed in terms of kg per meter cube, and g is nothing but meter per second square. So kg meter per second square is nothing but 1 Newton. So Newton per meter cube is the unit of specific weight. So be careful about the units and be careful about the definition and the formulas. Right? Now I'm going to give the fourth one. I'm going to give the fourth one. That is nothing but specific gravity. It is indicated by symbol S. I'm going to I'm going to compare the weights of all fluids with respect to standard fluid. That is, I'm going to compare the specific weights of all liquids in our nature with respect to standard fluid. What is the standard fluid here? Water. As same as I'm going to compare the specific weight of all gases with respect to specific weight of standard gas. What is the standard gas here? That is nothing but air. So I'm going to compare the weight, specific weights of the two fluids. That is, one is standard fluid, one is any type of fluid. Now I'm going to write the definition or formula. That is the ratio of specific weight of any fluid divided by specific weight of standard fluid. This is the definition of specific gravity. But here, in case of specific gravity, I'm going to apply for two types of fluids. One is in the form of liquid, one is in the form of gas. So I'm going to apply this formula for liquids and gas. I am writing specific weight of liquid is equal to how much you get it? That is specific weight of liquid divided by specific weight of water. Why? Because specific weight of standard fluid in case of liquids or water. What is the specific weight here? Formula is rho g for any fluid, rho into g of any liquid divided by rho into g of water. Then here Gg both are cancelled. Sorry, Gg both are cancelled. Then I'm writing here density of liquid by density of water. So that is the formula of specific gravity of liquids. Right? Now I'm going to write it. Write it. What is the specific gravity of gases? What is the specific gravity of gases? I am writing here specific gravity of gases is equal to, directly I can write it, specific weight of any gas divided by specific weight of standard gas. What is the standard gas here? Air. What is the standard gas here? Air. So then I am writing here rho of any gas divided by rho of air. So this is the formula of specific gravity of gases. Specific gravity of gases. So please take care about those 2 points now. So this is the another properties. One is specific weight of the fluid and one is nothing but specific gravity. And now four properties are density, specific volume, specific weight, and specific gravity. And next one is the property number 5. It is the very important point in all competitive exam. That property is nothing but viscosity. So most of the gate questions in this chapter asked on viscosity. So all the problems are involved with viscosity property. So now I'm going to explain what is viscosity. So I'm writing here. So here property number 5, viscosity of fluid. Now listen carefully. What is the meaning of viscosity? What is the meaning of viscosity? So if you take a fluid, I'm giving with example. I'm going to explain with example. So please take care about the example. If you know what is the meaning of viscosity, automatically we can write the formula and we can write the units also. So listen carefully what I am saying. What is the meaning of viscosity? How we can define it. So I am taking a boundary. Boundary is nothing but a fixed surface. I am taking a boundary which is a fixed surface. This is the fluid which is passing over the boundary in this direction. These are the fluid particles. These are the fluid particles. These particles are contact to each other, but before passing over the boundary, all particles are moving with same velocity. That velocity is named as free stream velocity. Free stream velocity. Are you got my point or not? So before passing over the boundary, all particles are contact to each other and all particles are moving with the same velocity. Then it is having the velocity is named as free stream velocity. Named as free stream velocity. Now, when the fluid is passing over the boundary, what happens? So listen carefully. When the fluid is touches the boundary, when the fluid is touches the boundary or passing over the boundary, then what happens? When the fluid is passing over the boundary, this particle is contact the boundary here. Then what is its velocity? Tell me. When this particle is contact with this boundary, the boundary is said to be under rest, and this particle is also comes under rest when it is contact with the boundary. So this particle is said to be under rest and its velocity becomes zero. Why? Because the boundary velocity is also zero. Then what is the fluid particle which is contact with the boundary is also is equal to zero? Is also is equal to how much? Zero. Then what about the this particle which is above this particle? This particle not contact with the boundary. This particle does not contact with boundary, but this particle is contact with this particle. But this particle velocity is never equal to zero. If it is contact with boundary, this particle velocity is also zero. But this particle is contact with this particle. That means this particle is under motion. This particle is under motion. Are you got my point? So if you see these two particles, one particle is under rest, one particle is under motion. So it is having some velocity. This velocity is how much? Zero. It is having 1 meters per second velocity. If you take another particle above this, if you take another particle above this, if you take another particle above this, it is having 2 meters per second velocity, 3 meters per second velocity, 4 meters per second velocity. Now what you observe now? What you observe now? So at the bottom of the boundary or at the surface of the boundary, velocity becomes zero. Velocity becomes zero. Now tell me, when the number of particles are increases above this particle, then this total weight of the particle is acting on this particle or not? These are the four persons. This is one person. This person is always carries these four persons. These are the four particles having weight. This total weight of the four particles which is acting on this particle. So where the pressure is maximum here, the pressure is maximum here. So if you take this particle, only three particles above this particle, so pressure reduce. So if you take this particle, on this particle above only two particles, pressure is reduced on this particle. If you take this particle, on this particle, above this particle, we are having only one particle. So the pressure on this one is less. And what is this particle? This particle is free particle. So the pressure on this particle is nothing but atmospheric pressure. This particle, the pressure on this particle is nothing but atmospheric pressure. Now, if I am saying very clearly, when a fluid is passing over any solid surface or boundary, solid surface or boundary both are same. When a fluid is passing over any boundary, at the boundary velocity becomes zero, pressure is maximum. At the free surface of the liquid, that is at the top surface of the liquid, velocity is maximum, pressure is minimum. Pressure is minimum. When depth of water is goes on increases, or when depth of fluid is goes on increase, pressure is goes on increase. I'll give the explanation very easily in statics how to calculate the pressure at every point when the fluid is said to be under rest or when the fluid is said to be under motion. I'll give the explanation very clearly, right? But here we are going to discuss about the viscosity. So we can easily understood this particle is under rest condition, this particle is under motion. Then what happened here? Then what happened? The velocity goes on increase. Velocity goes on increase here. And the pressure is goes on reduces here. Right? Pressure is goes on reduces here in the upward direction. Pressure is reduces, right? In the upward direction. Now here, what I am saying very clearly, when the particle is said to be under rest condition, this particle is said to be under rest condition. This particle is said to be under motion. Right? Very clear. This particle always try to bring this particle into motion. Why? Because these two are contact to each other. These two are contact to each other. When these two are contact to each other, these two particles are same or different. These two particles are same or different. These two particles are same particles. Then the force of attraction between the two same particles is named as Cauchy forces. The force of attraction between two same particles is named as Cauchy forces. If there is no Cauchy forces here, or if there is no contact here, there is no velocity variation. There is no velocity variation. All are moving with the same velocity. I got my point or not? That means if this particle does not contact with the boundary, all particles are moving with the same velocity. Once this particle is contact with the boundary, then this velocity becomes zero. Velocity goes on increase from bottom to top. So what happened here? This particle is under motion. So this particle is under rest condition. This particle always applies some force on this particle in this direction to bring the particle into motion. At the same time, this particle also applies some force on this particle in this direction to reduce its velocity. To reduce its velocity. Have you got my point or not? So simply we can write very easily. So listen carefully. I'm going to indicate this particle apply the force. This particle apply the force on this particle in this direction. At the same time, this particle applies the force on this particle in which direction? In opposite direction. So both are having equal magnitude and directions are opposite to each other. Such type of force is named as shear force. I have already told you what is the definition of fluid. Fluid is a substance which deforms continuously under shear forces or under shear stresses. So listen carefully. Here there must be shear between the fluid particles due to which one? Cohesive forces. When the cohesive forces are exit between the fluid particles, there must be a rate variation of velocity between particle to particle. So if we can easily understood velocity varies from bottom to top and top to bottom due to the cohesive forces between the particles. So simply I am saying here between any two fluid particles. So this particle is rest, this particle is under motion. This particle applies some force on this particle in this direction, and this particle applies some force on this particle in this direction. That means this boundary or this particle, both are same. Why? Because both are set to be under rest. So this particle applies some force on the boundary in this direction, and the boundary also applies some force in opposite direction. So at the boundary, if you take the boundary, on the boundary, the fluid always applies the force in this direction. Why? Because the fluid is said to be under motion. The fluid is said to be under motion. This fluid always try to bring this boundary into motion, but the boundary is always fixed. But boundary also applies some force on the fluid, which is in opposite direction to reduce the velocity of the fluid, or to reduce the motion of the fluid, or to retard the fluid. Then we are having equal and opposite forces between the particles or between the fluid and the boundary. Between the fluid and boundary. Between the particles, which forces exist now? Cohesive forces here. Cohesive force here. So due to the existence of the cohesive forces, there must be a shear will develop. Now, this force is same between all particles or different? I am asking to you, this force between these two, these two are same or not? I'll give the explanation. Same or not? That is not same. Why? Because all particles are moving with different velocities. So between these two, between boundary and between these two particles, this one and this one, 1 meter per second. Between boundary and this particle, 2 meters per second, and between this particle and boundary 3 meters per second, and between this particle and boundary 4 meters per second. So what I'm saying, when the velocity variation goes on increases, shear force is also goes on increases. Or you got my point or not? Shear force also goes on increase. Between these two, shear is less. Between these two, shear is increases. Between these two, shear is increases. Shear is increases. So shear is goes on increases from top to bottom. Or you got my point or not? So when the velocity variation is more, when the velocity variation is more, then automatically the shear is also vary. So what I am saying here, so listen carefully. So this velocity variation may be a linear, that means a straight line, or the velocity variation is belongs to parabola, or the velocity variation is belongs to a curve, or a cubic curve, parabola, linear, or so different types of fluids follows different types of velocity profiles. In our nature, we are having different fluids. Those fluids which are passing over any boundary, they are following different types of velocity profiles. So that means linear profile or parabolic profile, cubic profile or a curve. So there are different types of profiles we are getting. Now, how the profile we are getting here? So how to draw the profile? Now, I'm going to give it to you very clearly. I'm writing here when the force between the two particles increases, shear force is directly proportional to change in velocity. Change in velocity is nothing but du. That means this variation between these two is nothing but du, any two particles. Right? So this force must be acting on some area. This force must be acting on some area. So I'm going to divide by this area is equal df by dA is directly proportional to du by. The velocity varies in which direction now here? Y direction. The velocity variation in which direction? Y direction. So the velocity changes with respect to dy. The velocity varies with respect to which direction? Y direction. Now I'm going to write it. This one is named as shear stress. Force by area, that is stress. But here, which type of stress is exit here? Which type of force here? Shear force. Shear force by area, we are getting shear stress. So I'm writing shear stress tau is directly proportional to. This one is named as velocity gradient. Velocity gradient or rate of shear strain. Rate of shear strain. So I'm writing here du by dy. It is named as a rate of shear strain. Rate of shear strain or velocity gradient. A rate of shear strain or velocity gradient. Right? Now here I'm going to give it to you. So if you want to remove this proportionality limit, we are going to put a constant. What are the constant we are having here? Now I'm going to take it here. Tau is equal to mu into du by dy. That is the constant we are going to put between the shear stress and the rate of shear strain. So mu is named as dynamic viscosity. Dynamic viscosity. Now this is named as Newton's law of viscosity or law of viscosity. Both are same. This is named as law of viscosity or law of viscosity or Newton's law of viscosity. It is named as Newton's law of viscosity or law of viscosity. So Newton's law of viscosity or law of viscosity. I got it. So I will come back with one minute right here. 1 minute, please. Right. Now, what I am saying here, so law of viscosity. This is named as Newton's law of viscosity. Right. So that is named as Newton's law of viscosity or law of viscosity. So we have to write the formula for Newton's law of viscosity. This one. Now I'm going to write the what are the units of dynamic viscosity now. So now tell me here, what is the reason for reducing velocity here? The reason for reducing velocity is nothing but force of attraction between the particles. The force of attraction between the particles is nothing but cohesive forces. Now, in case of liquids, viscosity is due to cohesive forces. I'm writing here, viscosity in liquids is due to cohesive forces. Is due to cohesive forces. So please take care. Now I want to write the what are the units of dynamic viscosity. I want to write what is the dynamic viscosity. So this is the mu value. Mu is equal to so du by dy divided by that is mu is equal to shear stress divided by du by dy. D by dy. Now what is the formula for stress here? Stress is equal to force by area divided by du by dy. What is the force units? Newtons. Area is meter square. Velocity is nothing but meters per second. And y is nothing but meters. So we are getting Newton second per meter square. Newton second per meter square. This is the unit of, so this is the unit of dynamic viscosity. Now the viscosity is measured in points. Another form of units of viscosity is poise here. So I'm writing here 1 poise is equal to how much? 1 poise is equal to, these are the units now. These are centipoise. 1 poise is equal to 1 by 10 times of Newton second per meter square. Or we can write 0.1 Newton second per meter square. Or 1 Newton per second square is equal to how much now? I'm writing here 1 Newton second per meter square is equal to how much? 10 poise. 10 poise. And 1 centipoise is equal to 1 centipoise is equal to 1 by 100 times of poise. So these are the values of poise and centipoise. So viscosity is measured in poise or centipoise, or we can express in terms of Newton second per meter square. So please take care about those two things now, right? So this is the definition of Newton's law of viscosity, Newton's law of viscosity, and what is the reason for viscosity in liquids, and what is the formula for dynamic viscosity, and what is the limits of dynamic viscosity. So this is clear. Now I'm saying here, what is the meaning of viscosity? Viscosity is the property of fluid which reduce the velocity when it flows over the another fluid. Or we can say simply, viscosity is the property of the fluid which pose the motion of the one fluid layer which flows over the adjacent fluid layer, which flows over the adjacent fluid layer. That is always named as viscosity. So viscosity, simply we can say viscosity always reduces velocity due to forces which is present in fluid particles. That is nothing but opposing forces in case of liquids. But in case of gases, what is the reason for viscosity? Gases, all particles are far away to each other. They are moving in randomly. Then they are going to collide to each other. So they are going to collide to each other. When the particles collide to each other, what about their velocities now? When the particles are collide to each other, the velocity reduces. The velocity will also changes. So the velocity changes means reduce in velocity. Reduce in velocity. So reduce in velocity in gases due to molecular collision. Due to molecular collision or momentum exchange between the one particle to another particle. So here I am saying very viscosity in liquids is due to coercive forces and viscosity in gases due to molecular collision. Molecular collision. So please take care about that thing now. Right? Molecular collision. So now I'm going to give it to you. So according to Newton's law of viscosity, how many types of fluids we are having? And what is the stress strain diagram of those types of fluids? So actually we are having two types of fluids according to Newton's law of viscosity. So I hope you understood what is the definition of viscosity. Viscosity is the property which oppose the motion of the fluid layer which flows over the adjacent layer. That means it always reduces velocity. The velocity reduced due to coercive forces and as well as with the molecular momentum exchange or molecular collision. Right? Now here, what is the for Newton's law of viscosity? So I'm writing here tau is equal to mu into du by dy is named as Newton's law of viscosity or Newton's law of viscosity. Is it right or not? Right. Now, what I am saying here, what are the types of fluids? What are the types of fluids according to Newton's law of viscosity? Now, then here, according to Newton's law of viscosity, fluids are classified into two types. First one is named as Newtonian fluid. Second one is named as non-Newtonian fluid. First one is named as Newtonian fluid. Second one is named as non-Newtonian fluid. So in case of Newtonian fluid, according to Newton's law, we are writing W is equal to W is directly proportional to how much du by dy means the shear stress and the shear rate of shear stress both are directly proportional to each other. That is, both are linear. It implies tau is equal to mu into du by dy. Both are linear function. That is the definition of Newtonian fluid. Next example is nothing but in case of Newtonian fluid example, water and air are the best example for Newtonian fluid here. Next example for Newtonian fluid, right? Now, what is the non-Newtonian fluid? Non-Newtonian fluid means the fluid which does not follow the Newton's law of viscosity, then the fluid is named as non-Newtonian fluid. But it follows another equation. I'm writing that equation tau is equal to tau naught plus mu into du by dy whole power n. Whole power n. Right. So now in case of non-Newtonian fluids, so this fluid does not follow the Newton's law of viscosity. Newton's law of viscosity. Right. So in case of non-Newtonian fluids, the non-Newtonian fluids are again classified into two types. What is the difference between these two equations? Here only two terms, tau naught and then or two additional terms we are having in that equation. But tau naught is nothing but initial shear stress. Tau naught is nothing but initial shear stress. Initial shear stress. A little bit initial shear stress means the fluid having stress between the particles without application of the external force before going to deform the fluid. Actually, the stress is always developed inside the fluid by the application of external force. But in our nature, we are having the some fluids having initially some stress. Initially having some stress without any application of force. Best example is paints, gel. So there are different types of fluids are there. After application of the force, the fluid deforms. After application of the force, the fluid deforms. When n is equal to 0, it is linear. When n is greater than 1 and less than 1, it follows a curve. So it is having initial stress or after application of the external force, the shear and the strain both are follows the linear or non-linear. So we are having two terms here. Initial shear, after application of the force, there must be a shear. Without application of the force, this is nothing but initial shear. After application of the force, this is the strain value which is developed inside the fluid. That varies linearly or non-linearly depending on the n value. Depending on the n value, n is equal to 1, it is linear. N is greater than 1 or n is less than 1, it is non-linear. So I will give it to you one by one. When n is equal to 1, which type of fluid it is. N is greater than 1, which is type of fluid it is. N is less than 1, which type of fluid it is. I will give one by one very clearly. So please take care about these points. So here non-Newtonian fluids are two types. That is first one. time independent. Time independent. And next one is nothing but time dependent. Time independent. Next one is time dependent. So what is the meaning of time independent? Time independent means the viscosity of the fluid does not change with respect to time. That is, simply we can say d mu divided by dt must be equal to G. That is, viscosity remains constant. There is no change in viscosity with respect to time. That fluid is named as time independent. Time independent fluid. And a time dependent fluid, we can say simply that is viscosity must be vary with respect to time. That is nothing but d mu divided by dt is not equal to. That is named as time dependent fluid. Now, in the case of time independent fluid, again we are having three fluids. We are having three fluids here. So please take care about the fluids. In case of time independent fluids, we are having again three types of independent fluid. That means this cost of the fluid is remains constant. It does not change with respect to time. So three fluids come under the condition. That is first one is nothing but dilatant fluid. So one is dilatant fluid. And the second one is pseudoplastic fluid. And the third one is nothing but Bingham fluid. Third one is nothing but Bingham fluid. And time dependent fluids are two types. Time dependent fluids are two types. One is thixotropic fluid. Thixotropic. And next one is nothing but rheopatic. So these are the different types of fluids which comes under non-Newtonian fluid. Now totally how many fluids we are having here? So we are having first one Newtonian, next one dilated, next one pseudoplastic, next one Bingham, next one thixotropic, next one is rheopatic. So this is the classification of fluids according to our Newton's law of viscosity. So according to the law of viscosity, some fluids follows Newton's law of viscosity. Those are named as Newtonian fluids. Some fluid does not follow Newton's law of viscosity, so those fluids are named as non-Newtonian fluids. They follow relation. That relation is given here. So according to non-Newtonian fluids, again classified into two types: time independent, time dependent. Time independent means viscosity does not change with respect to time. And time dependent means viscosity must be changed with respect to time. So this type of fluids are named as time dependent and time independent fluids. Now I'm going to give it to you how to draw the stress strain diagram for different types of fluids. Stress strain diagram of different types of fluids. Now listen carefully how to get those diagrams here. So I'm going to write as same as in our strength of material, how to draw the stress strain diagram of mild steel and stress strain diagram of brittle material. And the stress strain diagram of different types of material we can write very easily. So same as here also, I'm going to write the stress strain diagram for different types of fluids according to Newton's law of viscosity. Right, I'm writing here stress strain diagram of different types of fluids. So stress strain diagram of different types of fluids. Now listen carefully. So first of all, I'm going to write it. First of all, types of fluids. First one is nothing but ideal fluid. Ideal fluid. And the second one is nothing but dilatant fluid. Third one is nothing but pseudoplastic. And the fourth one is nothing but Bingham fluid. And fifth one is nothing but isotropic fluid. And sixth one is nothing but rheopatic. Sixth one is nothing but rheopatic fluid. Now I'm going to give it to you. So what are the equations belongs to fluids? These fluids are defined by the different conditions. These fluids are having names given by under different conditions. I will give it to you how they are named as dilatant, how they are named as pseudoplastics, how they are named as Bingham. I'll give one by one. Please take care about those points now. This viscosity property is very, very important in GATE and IE's point of view. So, any competitive exam, so you have to take care about this viscosity property. Right. Now, in case of ideal fluid, in case of ideal fluid, according to Newton's law of viscosity, ideal fluid does not have any viscosity. That is, mu is equal to how much? Zero. That means tau shear is equal to zero. Why? Because tau is equal to mu into du by dy. It does not have any viscosity. If mu is zero, automatically shear is also zero. Shear is also zero. So please take care about that. So these conditions are belongs to ideal fluid. So there is no such type of fluid which exists in nature. All fluids are named as real fluids. So if you see this one, all are belongs to real fluids. All are belongs to real fluids. Or you got my point out. Now I am saying what is dilatant fluid? What is dilatant fluid? This fluid follows some condition like this. First one, tau naught is equal to zero. Tau naught is equal to zero, but n is greater than one. This is the condition followed by this fluid, and the fluid is named as dilatant. These are the condition. This is the condition followed by the fluid. Those fluids are considered dilatant. Now, if we substitute this condition, the basic equation of non-Newton fluid. So this fluid follows this equation. Tau is equal to tau naught plus mu into du by dy whole power n general. Now, if substitute this condition, we are getting tau naught is equal to 0, this value is equal to 0, but this value is greater than 1. Then I'm writing here tau is equal to mu into du by dy whole power n is greater than is the mathematical equation for dilatant. So this is the condition for dilatant fluid. So please take care about this condition. What in our nature, some fluids follows this condition, then the fluids are comes under dilatant fluid. And the second one, pseudoplastic fluids that implies so tau naught is also equal to zero. That is, there is no initial shear. The shear is always present by the application of external force for this fluid also. But remaining all are having initial shear. And here n is less than 1. N is less than 1. Then what the mathematical equation? Tau is equal to mu into du by dy whole power n is less than 1. So this is the condition followed by some fluids. Those fluids are comes under superplastic fluids. And the Bingham fluids. The Bingham fluids are the condition tau is not equal to 0. It is having some initial stress. It is having some initial stress. And n is equal to how much? 1. N is equal to how much? 1. Then the fluid is named as uniform fluid. And this mathematical equation is tau is equal to b into du by dy whole power n is equal to 1. That is nothing but tau is equal to tau naught plus tau naught is not equal to 0. So I am writing. Right. And in this case, tau naught is also not equal to 0, but n is less than. N is less than 1. N is less than 1. I'm writing tau is equal to tau naught plus mu into du by dy whole power n is less than 1 is the mathematical equation for isotropic fluid. Mathematical equation for isotropic fluid. Now, what are the rheopatic fluids here? These fluids are following the condition. These fluids are following the condition. That is, tau naught is not equal to 0, but n is greater than 1. Then tau is equal to tau naught plus mu into du by dy whole power n is greater than. So these are the mathematical relations for the different types of fluids, which are follows different types of conditions. And depending on the condition, we can define fluid. Right. So this is ideal. There is no such type of fluid exists in our nature. Remaining all fluids are named as real fluids. Right. So now one more one is there. That is Newtonian fluid also there. Newtonian fluid also there. Newtonian fluid is nothing but that is a fluid which follows the Newton's law of viscosity. Are you got no point or not? Right. So now I'm going to draw the stress strain diagram for these fluids. Now listen carefully here. So this is nothing but ideal. This is I'm writing ideal. This is dilatant. This is pseudoplastic, and this one is nothing but Bingham. This one is nothing but thixotropic, and this one is nothing but rheopatic. I'm going to draw the stress strain diagram for different types of fluids. That is nothing but these fluids. So that I'm going to take two axes here. I'm going to take two axes here. That is stress strain diagram for different types of fluids. So this is I'm taking x and y axis. So along x axis, along y axis, I'm taking two values. Along x axis, I'm going to take it as rate of shear strain du by dy per second. U by dy per second rate of shear strain. And here I'm going to write here shear stress. Shear stress value. Now I'm going to draw what is the stress strain diagram for ideal fluid. What is the ideal value for ideal fluid? Tau is equal to how much? 0. Tau is equal to, so where tau is equal to 0 on this diagram? So tau is 0 on the x-axis. Tau is 0 on the x-axis. So x-axis belongs to which fluid? Ideal fluid. X-axis belongs to which fluid? Ideal fluid. Now I'm going to write what is Newtonian fluid. In case of Newtonian fluid, tau is directly proportional to du by dy. So both are a linear proportionality. So I'm going to draw. So here is also tau naught is equal to 0. There is no initial shear. Initial shear 0 means this point is starting here. This is origin 0 comma 0. That means at that point there is no any shear. That is there is no any initial shear stress in the fluid. Usually stress is developed in the fluid by the application of external force, but without application of the external force also some fluids having stress. There is nothing but initial stress. But in case of Newtonian, that fluid does not have any initial stress. That's why I'm starting with this. But here, that fluid follows a linear function. That is, stress and strain both are linear. That is, n is equal to how much here? 1 generally, right? That is a linear profile for Newtonian fluid. Now I'm going to draw what is a delta. In case of delta, tau naught is 0. That is also starting from here. But n is greater than 1. N is greater than 1 means we are getting the curve like this. curve like this. So this is n is greater than n is greater than. So this is dilated. This is Newtonian. This is a Newtonian diagram. This is a dilated fluid diagram. So it's the profile, velocity, stress strain profile. And in case of Bingham fluid, this is the condition. Tau naught is 0 and n is greater than less than means we are getting the curve like this. This is n is less than 1. This is Bingham fluid. Bingham fluid. Now I'm going to, so this is pseudoplastic, sorry, this is pseudoplastic. Now third one is nothing but fourth one. Bingham fluid. Bingham fluid, it is having some initial stress. That means it is having initial shear. I'm going to indicate up to this one is having some initial stress. So up to this, it is having some initial stress. Tau naught. This line is belongs to tau. Or you got it? Right? It is having initial stress. After that, n is equal to means it is linear. Stress and strain both are linear. When n is equal to 1 means the stress and strain both are linear after application of the external force. So that is a linear function. So it is n is equal to 1. Have you got it? Right. Now I am writing here. So thixotropic fluid. N is less than 1 means we are getting the profile like this as same as n is less than 1. N is less than is thixotropic fluid. T. And next one is rheopatic fluid. Rheopatic fluid automatically we can draw like this. So this one is nothing but so rheopatic fluid. This one is Bingham fluid. So this is the stress and rate of shear diagram for different types of fluids in case of viscosity according to Newton's law. So here the horizontal line belongs to ideal, but what about the vertical line? Vertical line means here is viscosity zero, viscosity goes on increase, and at a particular point it becomes a solid. That means ideal solid. Vertical line is always belongs to ideal solid. Ideal solid. This is ideal fluid. Horizontal line is belongs to ideal fluid. Vertical line is belongs to ideal solid. So this is the stress strain diagram for different types of fluids. So I hope you understood very well. So for this analysis of viscosity, so I want to give it you one more point on this viscosity. Viscosity is due to cohesive forces in case of liquids. Viscosity is due to molecular momentum exchange between the particle and gases. So viscosity is a property which is always reduced velocity, which is always reduced velocity. So we can remember always viscosity always oppose the motion. Oppose the motion means it's always reduce the velocity. When the one fluid particle passes over the another adjacent fluid particle. So there must be a variation of velocity between the two fluid particles. Then there exists a force. The force is nothing but shear force. The shear force is directly proportional to variation of velocity. We can write the Newton's law of viscosity, law of viscosity. Then we can classify the fluids, Newtonian, non-Newtonian, and we can draw the stress and diagrams. Okay, I hope you understood this one. Now I'm going to give it you a simple point on this viscosity. So please take care of those 2 points also. Right. So what is the effect of temperature on viscosity? What is the effect of pressure on viscosity? So I'm writing here effect of temperature and pressure on viscosity of liquids or gases. Now, first of all, I'm going to explain what is the effect of temperature on viscosity of the fluid and what is the effect of temperature on viscosity of gas or liquid. So, first of all, I'm going to take it in case of liquids. in case of liquids. Now tell me, what is the reason for viscosity in liquids? Coercive forces. Coercive forces. So now when temperature rises, what happens? When temperature rises, the coercive force, that means force of attraction between the fluid particles, may reduce in some fluids, may increase in some fluids, but we are going to consider always the coercive forces reduce with increase in temperature. Such type of fluids we are going to use in the practical cases, because if velocity increases, automatically the power developed by the system is also increases. When the velocity increases here, when the viscosity reduces, velocity increases. Velocity increases, force increases. When force increases, work is also increases. Work increases, power is also increased. Power increases, efficiency also increases. So that this all are depends on viscosity of the fluid. So in case of water, the viscosity is very, very less. That's why the flow of water is more when compared to all fluids. So when the flow is more, velocity is more. It always supplies the maximum force on the component or any device. So which type of fluids we are going to use here? Which type of fluids we are going to use here means by increasing temperature, viscosity must be reduced. Such type of fluids we are going to use in case of practical cases. That means what are the fluids viscosity reduces by increasing temperature? So by increasing temperature, viscosity must be reduced. In some cases, viscosity also increases, but such type of fluids we are not used. For example, if you take a fluid which viscosity increases by increasing temperature, it never comes out of the pipe. If I, for example, I am taking one fluid which is moving in this direction and temperature is goes on increases, when the viscosity is also increases, then it becomes a solid. It becomes a solid. If it becomes a solid, it never comes out of this pipe. So that what I'm saying, we have to always use the fluids which is having decrease in viscosity with increase in temperature. I got the point. Right. Next one, in case of gases, in case of gases, this is what is the gases here? Molecular collision. Molecular collision. In case of molecular collision, by increase in temperature, if you take this is the gas, and this is the gas. If you increase the temperature, what happen here? The velocity of the particles will also increase. Why? Because they loses their density by taking the heat. By taking the heat, the particles of the gas losses their densities. When density losses, weight will also lose, and they are ready to move very high velocities. They are free to move with very, very high velocities. When the particles are moving with very, very high velocities, they are going to collide to each other and the velocity reduces suddenly. So that velocity variations are very, very rapidly increases by increasing temperature. So by increasing temperature, the viscosity of the gases will also increase, right? So in case of pressure, by increasing pressure, I'm telling in case of liquids, by increasing pressure, there is no any effect of viscosity most of the cases, but in some cases viscosity will increase. Viscosity will increase. So by increasing temperature, no effect on viscosity. So viscosity is constant. So there is no effect. But in case of gases, by increasing pressure, viscosity must be increased. Why? Because if you take this is the vessel, which is filled with a piston, and it is contains having some quantity of gas. If you compress it, that means if you increase the pressure, all particles are close to each other. All the most of the particles is reduced. So after some time, when the piston comes to this position, then there is no any space to move these particles. That means all particles are very close to each other. All are becomes acts as a solid particles. So we can compress the liquid, we can compress the gas up to certain limit only. We never compress the liquid or gas up to bottom of the cylinder. Or you got the point or not? We cannot compress or we cannot compress the liquid or gas up to the bottom of the cylinder. It means every gas, every liquid having some compressibility. I give it to you. What is the compressibility value in the next class and how to calculate and how to write the formula. So this is the property of viscosity. So you have to take careful about the property viscosity. This is very, very important for all competitive exams, not only for GATE and yes, so all competitive exams, there must be also questions on viscosity. So be careful about viscosity. Tomorrow I will continue the class. I will give the at what time we will start with the class. I'll give it to you. So thank you very much to all of you. I'm going to close the class. So tomorrow we will meet, discuss the remaining topics of on fluid properties, and we will continue the class. Thank you very much to all of you. Thank you.